let's continue with indeterminate forms. Remember that right now an indeterminate form is a situation where when we take a limit and we plug in x equals a, right, where we're considering limit as x approaches a of f of x, when we plug in x equals a, we get 0 over 0. Well, it looks like a percent sign, right? 0 over 0. Right, which remember isn't a thing, and it doesn't even give us a hint about what the answer could be. We've seen some cases where we got an indeterminate form and the limit did not exist. We've seen some cases where we got an indeterminate form and the limit totally existed. It just means we have to do more work. So remember, in the previous set of notes, the technique that we used was to factor the numerator and denominator. I'll just say top and bottom, and then cancel the common factor. And usually it's just one factor. I suppose it could be more. All right, so if we just take a look at a couple of these guys, let's just do a bunch of examples, right? Limit as x approaches 2. I always like to write it again. I think it's good form. But maybe what I could do is I could factor it, right? I could say, well, wait a minute. We can factor this into x minus 2 times x plus 1. And on the bottom is going to be x minus 2 times x minus 3. And oh, yay, we have a common factor, right? By the way, just looking at this, I hope you see we did get 0 over 0 if you plugged it in. So anyway, at this point, we just plug it in, and we get an answer of 3 over negative 1, or was that negative 3? Okay, great. Done. What about number 2? Well, I guess we have a limit. Let me write this one up here, too. Limit as x approaches 3 of, and again, I can factor this guy. Oh, I guess it is the same thing as before, so we sort of know already that it's going to factor. I again should point out that we do, in fact, have 0 over 0 when we try to plug it in. And again, we can cancel out this common factor. And, oh, actually, you know what? Never mind. Scratch that. We actually don't get 0 over 0. I lied. When we plug this in, what do we wind up getting? We wind up getting 3 and 9. So I think we get 4 over 0, right? Yeah, I think we get 4 over 0. Or, no, yeah, 4 over 0. Right, so actually in this situation, it looks like we're headed toward an infinite limit. Now, you could keep it the way it is, but I would still recommend canceling out by the common factor. It just makes things a little bit easier. So anyway, in this case, we have to do the left hand, right hand gig, right? We say, okay, left hand, limit as x approaches 3 from the left, and we can use the reduced fraction, and I would strongly recommend doing that, right? It's just easier, all right? Now what's happening? Top is positive, the bottom is negative, and we get negative infinity. For the right-hand limit, we do the same thing. And we get a positive top and a positive bottom in this situation, and we get infinity. So our limit, and again, we can use just the reduced fraction. Does not exist. All right, that's the end of that. All right. Similar situation here, right? What do we get here? So if we plug this one in, I think this one we do get 0 over 0, right? So here we get 0 over 0, and we're going to factor out an x squared, x plus 1, x plus 1 squared, so I'll just write it twice, and oh look, we get 0 over 0 because we have this extra x plus 1. So another situation, right? Another situation where we have an infinite, right? We get 1 over 0, right? So we're going to get an infinite left, right hand limit. Just the question is what's happening. So let's take a look here. If we do the left-hand side, we're going to get the limit as x approaches -1 from the left of x squared over x plus 1. And if you see that the top is always going to be positive, the bottom, let's be a little careful. If it's less than -1, it's like -1.1 or something, that means the bottom is negative. So I think we're getting negative infinity. Let's do the right-hand limit. And we're getting limit as x approaches -1 from the right. It's like -0.99 or something. And this is going to give us positive infinity. Okay, so once again, the limit, like the double-sided limit, as x approaches -1 of x squared over x plus 1 does not exist. All right, moving on. Let's check out this example. This is a little weirder looking. And again, if we just plug in x equals 4, we sure enough get 0 over 0. This one may not be so clear how to factor. We didn't discuss this in the algebra review, but here's how you do it. You can factor out x minus 4, and you get x squared plus 4x plus 16. And it may not be obvious that you take a two-term polynomial and factor it into, 5 terms, but it turns out it works. You can just multiply it out and show that it works. Anyway, on the bottom we're going to get x minus 4 times x plus 3. And that will cancel. And so we're left with this, and then of course we just kind of plug in 4 and we get 16 plus 16 plus 16, that's 48 over 7, and that's our answer. So I just want to reiterate that sometimes indeterminate forms lead to limits that exist, sometimes they lead to limits that don't exist, and there's no way to know until you cancel out that common factor. Now let's see what's going on with number 5. Number 5, sure enough, you plug it in, you get 0 over 0, but what the heck is with that square root? And the weird thing is, it doesn't look like we can factor anything out. And really, it doesn't look like we can. So instead, we're going to do the opposite. We're going to multiply by a common factor. So I'm going to rewrite this. Limit as x approaches 2 of this square root guy minus a number, right? And the annoying thing is we can't really even simplify this. We can't do anything about this, right? Square roots don't work well with addition and subtraction. But what we can do is we can get rid of this ugly radical on the top, and I guess we sort of introduced one on the bottom, but it's still okay. We get rid of the radical on the top, we simplify the top, and then we, once again, factor out the top and cancel it with a common factor on the bottom. So what we're going to do is multiply by the conjugate. And of course, whatever we do to the top, well, we have to do to the bottom. So I'm going to write multiply the top and bottom by the conjugate. All right. So this is going to give us limit as x approaches 2 of, so pause the video and see if you can factor that, or FOIL it out. So it's going to wind up being x plus 2, right, because the radical goes away. It's x plus 2 times radical x plus 2. The radical goes away. And then the difference between two squares means that the OI part of the foiling actually cancels it out, and then negative 2 plus positive 2 times positive 2 equals negative 4. Okay. Meanwhile, the bottom, please, please, please do not simplify the bottom. It's a bad idea. It's a waste of time, and it actually makes things more complicated. Okay, so we get this. I'm going to continue this over here. Note that we can simplify the top to x minus 2. See what we do right there? And then on the bottom, we still have that x minus 2. Oh, good thing we didn't simplify the bottom, right? And now we cancel out the top and the bottom. And just to be clear, when we do that, we're left with 1 on the top. And then we plug in x equals 2, and sure enough, we get an answer. I think it's 1/4. Maybe not what I would have expected, but that's what we get. Okay. Another example. All right, same sort of deal right here. And right, just to point out, we will in fact get 0 over 0. So what we're going to do is we're just going to rewrite this guy. And then I'm going to, we're going to multiply by the conjugate. Right? So when we do this out, we're going to get limit as x approaches -3. Let's FOIL this out, and we get x plus 12. That's the f part of foiling. The oi part of foiling is positive 3 times that, minus 3 times that. You see how they cancel each other out. So that goes away, and we're left with minus 9 on the top. Again, do not simplify this on the bottom. Just keep it separate. All right. And so again, we can reduce this. By the way, if you can just go straight to this next step, then please do. I just want to write all the steps in an abundance of caution. Oops, sorry, that's a plus, isn't it? Yeah, x plus 3. You know that the factor in the top has to equal the factor in the bottom, or else this problem wouldn't work out. And so we just cancel it out. Sure enough, we get positive 1. And then we just plug in our answer, and we get 1/6. Again, probably not what I expected, but that's what we get. And that's what we've got.